Thank you, everyone, for coming. Welcome to our next talk, Distance Metric Learning and Mutual Funds Categorization, to be delivered by Dr. Dhagash. I want to read a little bit of bio about Dr. Dhagash so we can know our speaker. So, Dr. Dhagash Mehta is a Senior Investment Strategist Manager, Machine Learning and Asset Allocation at the Investment Strategist Group at Vanguard. Prior to that, he was a principal research data scientist at Vanguard. Dr. Mehta is an editorial board member at the Journal of Financial Data Science. He pursued his undergraduate studies in physics in India, followed by part 3 of mathematical triples at the University of Cambridge, and PhD in theoretical particle physics from the University of Adelaide, Australia, as well as Imperial College London. Before joining Vanguard, he was a senior research scientist at United Technologies Research Center, and prior to that, a research professor at Department of Applied and Computational Mathematics and Statistics at University of Notre Dame. He has held multiple research positions at various research institutes, such as Fields Institute in Toronto, Simons Institute for Theory of Computing at Berkeley, the University of Cambridge, Imperial College London, the University of Adelaide, Australia, North Carolina State University, and Syracuse University, and the National University of Ireland, Maynooth. Dr. Mehta's areas of expertise are theory of machine/deep learning and applications of machine learning. In particular, he has published 75 plus research papers in reputed journals on optimization, computational algebraic geometry, numerical analysis, network science, and machine learning to solve various problems arising in financial services and wealth asset management. And in the past, power systems and control theory, theoretical physics, jet engines, and smart building system. Quite an impressive CV. So Dr. Mehta, we have you on for the next 30 minutes to discuss distant learning, distant metric learning for funds. I just want to inform our participant that if you have any question to ask, you can put that in the chat box. I'll relate that to Dr. Mehta at the end of the talk. So Dr. Mehta, we have our attention.
Yeah, thanks very much. And you can still see my slide in full screen mode, and my voice is fine, everything fine, right?
Yeah.
Okay, perfect. So thanks very much, Franklin, for that kind of introduction. Also, thanks a lot, David, for having me here. He also mentioned me in one of the previous talks, so I have more responsibility here to provide even more information from my talk. I'm going to talk about somewhat more technical stuff in this talk. I'll hopefully make it as clear as possible so that even the non-technical audience can also enjoy the talk, at least part of it. I'm going to talk about a niche area in machine learning called distance metric learning, which I applied for mutual funds together with a very, very smart and clever machine learning researcher, Dhruv Desai, who is my colleague here at Vanguard. So the title of the talk is Distance Metric Learning for Funds. I'm at Vanguard, the large investment management group. Although this work is mainly a product of our research on our own time, so don't get me in trouble. The work is just mine. Mistakes are also mine, not of my companies. So let's start. So I am interested in this particular problem, which is largely defined as product similarity in many areas of businesses, not just finance, but even many other areas such as Amazon or Google, recommendation engines and stuff. So the specific questions I'm interested in here are, given a specific product, what are other similar products? Okay. Other way around, the second question, if you are given two products, how similar these two products are from each other, or maybe how different they are from each other. Product similarity is also known as peer analysis, competitors analysis in the financial domain. Many people use these terms. A very frequently arising problem in all the areas of businesses, such as if you search for some specific product on Amazon, it will then start recommending some similar product. How do they define similarity? That's a whole point here of this talk. Okay? So in our domain, in the financial domain, in my case, what I mean by product is not necessarily a t-shirt or a shoes, but here in my case, a product means a mutual fund or any. The purpose of this talk, I'm just combining these mutual funds and ETFs into one word, fund. And I know that they are different, of course, but for the purpose of this talk, it's fine. So if you have one particular mutual fund that you are interested in investigating, this product similarity means that I should be able to come up with other mutual funds which are similar to the one that I'm investigating. Okay, so that's the product similarity in my case. What are the applications of such a product similarity tool? Let's say you have some sort of hypothetical product similarity tool for mutual funds. What can you do with this? Lots of applications, starting from sales and marketing, where if a salesperson goes through an end investor and he sees that this end investor has some of your competitors' mutual funds, then the salesperson can run the similarity tool and identify a similar fund to the one that the investor already has. But now the similar fund is a homegrown product, and then the salesperson can start pitching the homegrown product by saying that this is still similar product, but then there are many other advantages. For example, low expense ratio, better Morningstar rating, better brand name, and so on. So sales and marketing, immediate application. Alternative portfolio construction. Let's say you have some portfolio of mutual funds which is made of all of your competitors' mutual funds, and you want to create an alternative portfolio which has same risk return profile, but now you want to have it created using just your own mutual funds, okay, homegrown mutual funds. Again, you can run this kind of product similarity tool, and of course, on top of it, you might want to do some further analysis, but this is a very good start. Competitors analysis, a fund manager, whoever is running a particular mutual fund or ETF would always like to keep in touch with all the what other competitor funds are doing. So it's basically peer analysis in the financial domain. And again, you can run this product similarity tool, identify all the actual peers or the competing funds, and then you can try to compare or contrast performance and so on. Tax loss harvesting. In some countries, at the end of the tax season, it is advantageous to sell certain funds to realize gain, realize loss for the tax purposes. And then immediately you can buy a similar fund to retain the same risk return profile of your portfolio. It's called tax loss harvesting. And you can, again, use product similarity tool there. Launching new products. Sometimes you just don't see any closely similar product to a particular fund which is picking up in the market. And then you have identified a gap in your portfolio. So meaning that you might want to probably launch a similar product to the one that is becoming popular in the market. Customer experience. So you can imagine some sort of dashboard where the customer and investor can play with all the similarity tool to create their own portfolios. And similarly, financial advisors can also play with this kind of tool to create a more mature, more diversified portfolio. Okay, many applications. These were just ones that I could think of for this talk. Given so many applications of this kind of product similarity computation or tool, you'd think that there might be some available solution. And of course, there is one. It's called third-party categorization. So, for example, Morningstar categorization, Lipper categorization for all these mutual funds. What happens is this categorization systems will provide category to each and every mutual fund in the market. For example, large blend, large cap, mid cap, and so on. Then when you have a particular fund under investigation, you are supposed to look up this categorization of the particular fund that you have in your hand. Go to the lookup table, say at Morningstar, and then identify all the other mutual funds which are in the same category. For example, if your first fund is large blend, you look up all the mutual funds which are categorized as large blend by Morningstar. All these funds will be your similar funds. Okay, so that it's very popular methodology. Both these systems. Sometimes the methodology for categorization is not fully disclosed. It is partially black box. Okay, so with this background, I realized a couple of years ago that there was quite some interest from machine learning side to come up with data-driven methodology to reproduce this Morningstar categorization. Okay, all the way in 1997. So people were writing papers on machine learning for mutual funds categorizations in 1997. There are actually many other papers in 2001, and then many others all the way till 2019. What they were doing was they would take many of the aggregate level information or aggregate level variables such as percentage allocation in retail, tech, energy sector, and so on, percentage fixed income versus equity, and so on. So for each mutual fund, you have all these numbers, all these variables. So it's a tabular data. And then they would perform unsupervised clustering, such as K-means, spectral clustering. Even people use self-organizing maps, which were very popular before the autoencoders, because they were also learning some embedded representations. So after doing clustering, they would try to map each of the clusters to the actual Morningstar categories for these funds. So, and with the hope that each cluster would be homogeneous with respect to the Morningstar categories, meaning that each cluster would have funds which are from the same Morningstar category. There will not be any other mutual fund in this cluster if Morningstar categorization system is reproducible using data-driven approaches. Okay, so that was their approach. They eventually were not finding these homogeneous clusters. What they were finding was that after this clustering, each cluster would have multiple categories funds. So there were inhomogeneous clusters, incomplete clusters, and then they were claiming that Morningstar categorization system was not proper. There was some flaw, and so on. Okay. And then I was reading these papers, and then I started realizing many things. And before talking about these, let's talk more about what similarity is from the math point of view. So as a first start, let's say you have some n number of variables, which means that you are talking about n-dimensional feature space or n-dimensional space. Okay. Each data point, each point in this n-dimensional space corresponds to a particular mutual fund. And then two data points would, of course, correspond to two mutual funds, two distinct mutual funds. The distance in this n-dimensional space between these two data points is essentially the the similarity, it gives you the similarity score between these two mutual funds. Okay, so again, the distance between two mutual funds in this n-dimensional space is essentially a similarity score or similarity in terms of math. That's what similarity means as a first pass. And then when I say distance, people usually think of Euclidean distance, right? So the Euclidean distance in n-dimensional space, it will give you similarity. Is it the only option? There are two counterexamples. One in Manhattan Street map, if you want to go from the point start to point end, and if you just take the Euclidean distance route, you cannot penetrate all the buildings across the way, right? So you have to take this perpendicular straight line and then again perpendicular line to reach from start to end. It's called the Manhattan distance. It is called Manhattan distance in even math. And it's a counterexample where Euclidean distance is not a good distance metric. The second example is if you want to travel from, say, Australia to India on the surface of the sphere, you have to be on the surface of the sphere. You cannot just use a Euclidean distance. Otherwise, you are assuming that you can penetrate the Earth, which is hopefully not possible. There are many different distance metrics available in the literature as well as in scikit-learn. In fact, you can come up with your own distance metric as long as your distance function just satisfies these four conditions. First, the distance cannot be negative. The distance is 0 if you are computing the distance between the same data point. If and only if it is 0. Okay? Distance is symmetric, meaning distance between x and y is also equal to distance between y and x. And there has to be this triangular inequality. If you come up with some distance function or function which satisfies all these properties, then you have define your own distance metric, and you can name it on your name. Okay, so here is my problem with all this previous literature, which were doing clustering for mutual funds, and they were claiming that Morningstar categorization system had some flaws. The problem is that all these previous researchers were using by default Euclidean distance. They were then hoping that Euclidean distance is all right. Here is my argument. You cannot do clustering using arbitrary distance metric such as Euclidean distance and hope to reproduce a classification, a categorization system. You have to use the distance metric that this categorization committee might have used. Of course, a categorization committee might not be starting with writing down the distance metric and then do all this categorization, but they do have something in their brains. They are using some solid system, some rule-based system. You need to extract the distance metric out of their brain, meaning out of their labels. Okay, so all you have is labels, in our case, categories. Can you reverse engineer the distance metric? So here is a proposed idea. Of mutual funds and their categories, learn the distance metric from the data. I do not know if I should be using Manhattan distance or Chebyshev distance and so on. What I want to do is I just want to learn the distance metric instead of guessing what the distance metric should be. Okay, so that's the philosophy. Once you have the correct distance metric, apply k-means, and hopefully it will reproduce all these Morningstar categories as clean clusters, even using k-means. So here is a precise question. Once you have all this labeled data, such as mutual funds aggregate level features and their categories, the categories are the labels, can you reverse engineer the distance metric such that this new distance metric respects the labels. In other words, in this new distance metric, the two data points which have the same category should be close to each other, and the two data points or two mutual funds which have different categories should be far from each other. Can I come up with that kind of distance metric that respects this relationship? That's the question. And one way to do this is to use a more generalized Euclidean distance form. One of the most popular general Euclidean distance form or parametric form of Euclidean distance is called the Mahalanobis distance. It is defined as this equation. So d of x, y, distance between x and y, is equal to square root of x minus y transpose times a matrix A times x minus y. Notice that if this matrix A was just an identity matrix, it would have reproduced the usual Euclidean distance, right? So once you have some non-identity matrix here, in between this x minus y transpose and x minus y, you have more generalized form of Euclidean distance, a parameterized form of Euclidean distance. And then there are many nice properties of this Mahalanobis distance metric. And P.C. Mahalanobis, he wrote this paper all the way in 1920s. And we are still using this. So it's very exciting to even cite those kind of papers which were written 100 years ago. Okay, so after Mahalanobis distance matrix, so you said that, okay, you want to start with this generalized form, and then you want to learn the numerical values of this matrix A using your data. And hence you have computed the distance matrix for your distance metric for your data, for your given data, okay? But how do you compute these numerical values of A? How do you compute the matrix A? And come in 2002, Nurips, Eric Jing, Andrew Ng, Michael Jordan, Stuart Russell, all the names that are very familiar these days, they wrote this paper where they showed how to compute the values of this matrix A. They just formulated this problem as an optimization problem. Here in the first piece, it just minimizes the distance between data points which are labeled as similar. Okay, so the first piece is just asking to minimize the distance between each pair of similar points, okay, which have the same category. The second piece is saying that no, if you have dissimilar data points, make them far. And the third one is more technical condition, so that on A, so that it is still a valid distance matrix. Okay, so that's the optimization formulation. Once you solve this optimization problem, you immediately get the matrix A, all the numerical values of each of the elements of the matrix A, and then you are done. Then you have computed the distance metric. Practically, you can use some of these Python softwares to do distance metric learning. Okay, so how does it work in this Morningstar or mutual funds problem? I used a snapshot of data, some of the usual aggregate level variables, equity, percentage, or percentage in certain industry, percentage in secondary sector, fixed income, and so on. There were also benchmark information in the data. Eventually, snapshot of a particular month, there were some 6,394 mutual funds and ETFs, and number of input features were some 3,000. We did PCA. The number of categories in this data was 53. So all these 6,300 mutual funds had 53 categories in total. And here is what I am comparing. I first want to do k-means with the Euclidean distance, which is what the previous researchers were doing. And next, I also want to do k-means, but now with this new distance metric that I learned using this Mahalanobis distance. Okay? And here are the results. That so the orange curve is showing the results for k-means using Euclidean distance. On the x-axis, I'm plotting the number of clusters, so k in k-means. And on the y-axis, I'm plotting different metrics. In the first plot, it is silhouette score, then DB score, inertia, and mutual information score. As you can now see, the orange curve not maximizing the silhouette score even at its peak. It's almost 0.4. And the peak is also at some 57 or so. So according to this computation, in silhouette score, the number of categories or number of clusters with k-means using Euclidean distance would have been 57, as opposed to the actual number of categories, which is 53. But when I use the Morningstar distance metric and then do k-means, bang on, I get all these categories reproduced as clean clusters. All these other metrics, other plots are also showing the same fact in different point of views. Essentially, this new distance metric with the help of k-means is reproducing each and every Morningstar category as a clean cluster. Okay, so that this shows the importance of the distance metric. Previous researchers were just following these orange curves. They should have done distance metric learning and then k-means. Okay, they did not even need any fancy techniques such as autoencoders or SOMs and so on. So I'll just conclude. I'm running out of time anyway. So identifying similar funds is a very rich problem in machine learning with lots of business applications. And second thing I wanted to highlight was distance metric learning. Very niche area in machine learning, is highly underappreciated. If you are trying to do some rigorous machine learning, you have to think more carefully about what distance metrics you are using. So I'll stop here. I'll take any questions.
Hi, thank you so much, Dhagash. We really enjoyed your talk. It was very informative and it was articulate. So thank you for coming with that talk. We have one of the questions here from Lalit Verma. If I would like to read it out for you, it says, wouldn't it be more accurate to use hierarchical similarities, those clustering, to truly compare funds?
True. So Morningstar categorization comes with multi-level categorization. So I also tried hierarchical clustering. Again, the same issue. I could not reproduce the Morningstar category at each level using hierarchical clustering. And again, the missing part was distance metric. So basically, if you use hierarchical clustering on the same data, it will give you some different clusters other than Morningstar categories.
Okay, thank you so much. Okay. So, okay, there's another question for now. Yeah, but I have a question I actually thought about. Maybe you covered it, but I didn't really take note of it. You mentioned that it's always good to start out without bias toward the distance metric. So you have to learn the metric to the data, right? So how do you learn a particular metric to use to the data? How does the data teach you that? Like, go to learn the particular metric to use for the data?
No, so if you have labels for your data,
right,
then it might be possible for you to learn the distance metric. If you just have truly unsupervised problem, where you do not have labels, then you are on your own. Then you have to use Euclidean distance, and Euclidean distance is as bad or as good as any other distance metric. Having said that, in some cases, Euclidean distance might still not be appropriate, even if you have truly unsupervised problem. For example, if you have only categorical variables, then Euclidean distance is not the right metrics. If you have mixed some continuous and some categorical variables, then also you cannot use Euclidean distance.
Okay.
So yeah, in those cases, you still have to worry about distance metric.
Thank you. I'll have a second question from Lalit again.
Sure.
Okay. Sorry, let me take this one since I've done from Lalit before. Colin Long is asking, do we have to select these mutual funds? Would this method work for mutual funds coming from different markets?
It should work for other mutual funds as well, as long as you have all the necessary variables. So if you have, say, mutual funds from Canadian market or maybe Australian market, you need to have corresponding variables as well, right? If there are some other nuanced variables, you also have to include them. As long as you have all the variables necessary to distinguish all these mutual funds, then this method should work.
Thank you. So maybe the first part of that question said, do you have to pre-select the mutual funds by yourself? Is it to be pre-selected?
No.
Okay. No problem.
No, you do not have to.
So, okay. Then I'll take another question from Lalit. Sure. Because the attributes themselves have their own hierarchy, you will have to allocation and retail for different stocks within the same. You take that into account.
Very good question. Yeah. So.
Wow. Okay.
Yeah. So what he's saying is that let's say you have percentage allocation in the Asia region, but then you also have percentage allocation in India, percentage allocation in China. So there is a hierarchy, right? You are already included the region, Asia, but then you also have India and China. So how do you deal with those kind of hierarchy in the variables? So we took only the lowest level variables. So in this particular example, I would choose only the percentage allocation in India, percentage allocation in China. And there is also documentations available for all this hierarchy of the data from Morningstar and Lipper as well. So I always chose the lowest level variables.
Okay. Thank you. So I hope Lalit got that. And then there's a last question from Lalit again. It says that the different categories you reduce over 8,000 funds to 53 odd categories. What were those? Are they on latent space?
I didn't get the question. Yeah.
Okay. Let me go over again. Says the different categories you reduce over 8,000 funds to 53 odd categories. What were those? Are they on latent space?
No, they are still on the original space because I still use the k-means in the same variables, right? The 53, I guess I still didn't get the question. That's why I'm struggling to answer the question. So 53 number, maybe, okay, let me clarify. So the number 53 came from the actual categories in the data. So all these 8,000 or 6,300 or something mutual funds had, in total, they were from 53 categories. And I reproduced those 53 categories. I did not have any new cluster.
Okay. Okay.
Yes, 53 clusters and 53 categories. So they matched. That's a whole point. The original number of labels or the original number of classes were reproduced by data-driven clustering, meaning 53 categories were reproduced as 53 clusters.
Okay. I hope Lalit is satisfied with the answer, or if she's not, she can answer us more. Okay. Okay. So just to know, is it okay to include your information here, your email,
Sure.
in case someone wants to reach you for the information?
Of course, and they can also reach me through LinkedIn if they prefer that way.
Okay, no problem. I'll include that here. Okay. I think Lalit is satisfied with the answer. That's good.
Okay.
Okay. So we don't have any more answer. Okay. Okay. Sorry, there's another question coming in from Lalit again. I don't know if you have more time for that, but let me just ask it now. You see, the Mahalanobis distance is typically used in outlier detection for n-dimensional, but you used it here for optimizing. Have any answer for that? Did you get a question?
Is it a question or a comment?
Yeah. Well,
yeah, okay.
Comment
so it's a comment. Yeah, true. So I'm using it to optimize and identify the right distance metric for my data. So I'm not using it for outlier detection. Yes, that's correct. Thanks.
Okay. Okay. No problem. Thanks so much. Okay.
I can hang around in the networkings or booths if they have further questions, or maybe it's up to you. I'm still here.
Okay, I think she's asking one more question. I think we'll take that one more question, then we'll leave. Okay. So you did unsupervised learning, right? Is that yes or no answer?
I cannot give you yes or no answer. It's trickier than that. So yes, I did unsupervised clustering, unsupervised learning. However, I used labels of the data, right? So it has a specific name. It is called supervised clustering. It is an oxymoron, but it is called supervised clustering. I used labels, learned the distance metric, and used it for clustering. So it is called supervised clustering.
Okay, thank you. I think she got that. She's saying thanks for that. It's also good to learn about the semi-supervised learning. That's good.
It is yeah, semi-supervised as well.
Yeah. How do you evaluate then if you use that?
So that's basically all these plots for clustering. Can you still see my slide, which has clustering metrics and results?
Right, you can see it.
So these are the metrics that I used to evaluate the final clustering.
Okay. Okay, thank you so much. Okay, so with the absence of further questions, we would like to a talk. You can reach Dr. Vamich on LinkedIn, or maybe through Dr. Dhagash on LinkedIn, or through the email. So thank you all for coming, and Dr. Dhagash for the nice and wonderful presentation. Thank you.
Thanks very much, Franklin.
Hello, can you hear me?
Yeah, hi. Can you hear me?
I can hear you. Thank you so much for the wonderful presentation.
Oh, thanks.
I was curious actually about it. It seems like a bit of a strange objective though to learn the distance metric. Normally you would want to try and improve the outcomes on a portfolio rather than to recreate the immediate rankings. I understand it was an academic problem before. It's strange. It's been a while since I used Mahalobus distance, but it's usually produced from the covariance matrices. You end up with that matrix A. That matrix A is no longer Mahalobus distance. It's just a weighted matrix for the measure, right?
So yes, that is correct. So I think this Eric Jing and Andrew Nugg, they presented this problem as an optimization problem to learn the values of A in the Mahalanobis distance metric.
Yeah.
So
in an arbitrary distance matrix of some sort.
Except that they also impose this constraint that A should be positive definite. So it still gives you more flavor of Mahalanobis.
Are you able to then extract any insight from matrix A apart from the?
That's a good question. Not yet. So to write a paper or for a presentation, I need a crisp story, right? This was kind of a crisp story in the sense that there was this heavily debated issue on whether Morningstar categorization is a rule-based system or not, and why they were not being able to reproduce them using purely data-driven way. What I came in and I said that they were not using machine learning correctly, in the sense that if you just use Euclidean distance and then expect that it will reproduce Morningstar categorization, which is a categorization system, that's apples to oranges comparison.
Yeah.
So it's just a nice story, but of course there are many other applications, as you already guessed.
Yeah. Do you think if you did some reduced ranking on the original labels, you could how do you think you could then continue on with the A to label unseen data?
By reduced ranking, do you mean some sort of PCA?
I mean, there's tens of algorithms for something like that, but because I mean, we're about to run out of time. Do you want to extend the time?
Sure.
So the challenge is you have all these individual elements for A, and you have this data-driven way to reproduce the labeling, but that won't allow you to create any further insights because every element you have corresponds to an entry in A. So, I mean, if you wanted to then go and categorize unseen data to include in your portfolios, you need a way to go from A to something that looks more like a translation for A, not for an element. Well, I guess you could use the original space. If you had some space that you, like the one you demonstrated, right? You could use because A is only in relation to the labels, right?
Yes.
So if you had your many-dimensional feature space that you built for composition based off of geography, equity, size, sector, all that stuff, do you think you could then take those labels those dimensions to figure out where a new equity would fall if it were to be included, but it doesn't have a corresponding rank in A. Does it make sense?
I didn't get the question. So let me tell you at least two interesting applications of this distance metric learned from Morningstar categorization. One is easy. If you have a brand new mutual fund, you don't know the category. How would you assign the category? And if you want to assign the category to this new mutual fund as if you are Morningstar expert panel, you just use this method. And it just immediately gives you the correct category. It can be actually useful for Morningstar itself to automate this whole process.
But I thought the way you've learned A only tells you things about the data that you put in relative to the labels, right?
Yes.
So if you had a new fund, right, say ETF XYZ, that isn't included in the that optimization process relative to pre-existing labels, it can't be assigned a weight in A.
It can. So if it is completely beyond all these 53 categories, then yes, then I cannot assign a good category. But if I assume that this new fund still can be categorized within the existing labels, then I can still do it, right? Then I'm fine.
Oh, so do you provide? So you have labels and you have 53 dimensions. Is that it?
No. So 53 is the number of categories.
Yeah, the number of categories.
And the dimensions is all this aggregate level features. Percentage equity, percentage allocation in retail sector, percentage allocation in tech sector, and so on.
So then you end up with this. You get the centroids out of your k-means, and you say which one's closest to the centroid.
Yeah.
And then you use that.
Yeah.
Okay. Yeah, that makes sense. Makes a lot of sense. Very exciting. Yeah. Well, thank you so much for sitting with me and helping me to think about it a bit more. Do you have? Are you going to be continuing work on the same project, or are you excited in others?
No, I think that this is still an exciting project. But I'm working on many other projects. Do you have finance background? Are you from the finance? Okay.
Yeah. Right now I'm working more on order flow and fun and exciting topics in trade by trade analysis and a little bit in volatility. But yeah.
And you are based in the US?
Or downtown Toronto.
Okay. Wow.
And for yourself?
I'm in Philadelphia.
Exciting.
So Vanguard headquarters is in Philadelphia. But we do have office in Toronto.
Are they nice people?
Yeah, they are nice people.
Good stuff. Well, yeah, thank you again so much, Dhagash. And I look forward to attending another presentation hopefully.
Yeah, thanks so much. Yeah, thanks so much. Likewise.
Take care.
Bye.